Welcome to everyone. I am Dr. Srinivas Rao, Professor, Triple E Department, Yashadhirrao Gottavalleru Engineering College, Gottavalleru, Andhra Pradesh. I am going to present you the topic per unit system. In this lecture, I want to discuss about what is the per unit system, how it is useful in power system calculations, and what are the different formulas involved in this subject. All those things I will discuss in detail. Power transmission lines are operated at voltage levels where the kilowatt is the most convenient unit to express the voltage. So in a power system, there will be many different types of equipment will be there. Motors, synchronous generators, transformers, transmission lines. So the voltage is generally high level operated kilovolt, and the rating of the machines will be generally in the range of kilowatt or megawatt. So because of the large amount of power transmitted, the kilowatts, megawatts, kilovolt amperes, and megavolt amperes are the common terms used. So when you use different computations of power transmissions and other calculations at different levels, so all these terms, the calculations will give very big numbers. So dealing these big numbers is very difficult and uncomfortable when you perform the different types of mathematical operations. So we are going to introduce the per unit system, which simplifies the computation, and it has also a greatest advantage related to transformers, which we are going to identify in the coming lectures. So actually the per unit value, it is defined like this. The per unit value of any quantity is defined as the ratio of the quantity to its base expressed as a decimal. So the per unit value is equals to actual value of the quantity by base value of the quantity. So for example, in a power system, if different voltage levels are there at transformers and machines, motors, so the biggest of all those things generally will be considered as the base quantity, and the actual quantity of the machine or will be considered as the actual quantity. So the ratio of the actual quantity to the base quantity is considered as the per unit value. So in the first, we will discuss about the various formulas that we will use, and various formulas we need to use, we need to derive related to single phase systems. So single phase system, computation of per unit values. So the per unit power is the actual power by base power, and per unit voltage, actual voltage by base voltage, per unit current, actual current by base current, per unit impedance, actual impedance by base impedance. So in this, the base power and base voltage are taken based on the best possible values we can select from the entire system. So, and from that we need to derive the base current and base impedance. In electrical engineering, the three basic quantities are voltage, current, and impedance. If you choose any two of them, the base or reference quantity, the third one automatically will have a base or reference value depending upon the other two. So base impedance is equals to base voltage by base current. So base voltage line to neutral. When you consider a single phase system, we will consider as line to neutral voltage. Base current, the base current value we need to derive. So directly we cannot take the base current value. Base current value depends on the base kVA and base voltage. So for base impedance calculation, first we should know the base voltage value and the base current value. And the base current value we need to compute based on the base power and base voltage again. So we will see how we will compute the base impedance in the next coming slides. The apparent power rating of the equipment will be chosen as the base power. So whether the machine rating is in kilowatts or like the transformers kVA, we will choose the best possible value of the apparent power rating of any highest generator as the base value generally. The base current can be calculated by the following expression. The base current is equals to base kVA by base voltage. So if the kVA is power is expressed in kVA, the voltage also we can express in kilovolt. So the base impedance value can be calculated like this. So base voltage VLN by 1000 into 1000 base current like this. So if you see, if you divide the base voltage by 1000, base voltage by 1000, we can express that in terms of kV. And base current is base kVA by base voltage. So we are going to derive the value of the base impedance here because we have already defined the value of the base current. Base current is defined as base kVA by base voltage. So we want to express the voltage in terms of kV. So base voltage is divided by 1000 and into 1000. So now base impedance, if you see that base kV whole square into 1000 by base kVA. See here in the previous slide, if you observe that base voltage, base impedance is equals to base voltage by 1000 into 1000 by base kVA by base voltage into kVLN. So the numerator term base voltage VLN by 1000 is this can be written as base voltage kVLN. If this goes to the numerator side, then we will get base kVLN whole square into 1000 by base kVA 5. And again, what we do is, so here base kVA we divide by 1000 and multiply with 1000 here. So this 1000 and this 1000 gets cancelled, and we will get finally base kVLN whole square. And since base kVA by 1000 is base MVA, the base impedance is equals to base kVLN whole square by base MVA. So finally the base impedance value is derived as base kVLN whole square by base MVA. So this is the finally the derivation of the base impedance. So the voltage should be expressed in kilovolts and the power rating must be expressed in megavolt amperes. So then the base impedance can be calculated directly. So actually what happens was all the formulas so far we have derived are considering all the data is given for a single phase system. But generally most of the systems are three-phase balanced systems. So the data is given as for the total three-phase system, and the voltage is generally given as line-to-line voltage. So the based on the data, the formulas, the base impedance, voltage, and base current, we need to derive these values in terms of three-phase quantities. So base power MVA is equals to base MVA three-phase by 3. So it is a balanced three-phase system. If you see this problem, for example, two generators rated at 10 MVA, 13.2 kV, and 15 MVA, 13.2 kV are connected in parallel to a bus bar. They feed supply to two motors of inputs 8 MVA and 12 MVA respectively. The operating voltage of motors is 12.5 kV. Assuming base quantities as 50 MVA and 13.8 kV, draw the reactance diagram. Here in this problem, all the values are given for a three-phase system. 10 MVA, it is a three-phase, the generator three-phase value. Total MVA or power rating of the machine. And 13.2 kV in general, it is a line-to-line voltage. It is not line-to-neutral voltage. So these two things we should keep in mind when we want to calculate the per unit impedances. The formulas so far we derived are considering they are for single phase system. So now we need to directly every time we need not derive the three-phase values into single-phase values. So we need to derive the formulas in terms of three-phase values for directly calculating the per unit impedance of the equipment. So base power is MVA single phase is equals to MVA three phase by 3, and base voltage KVLN is equals to KVLL by root 3. So the fundamentals. So now the per unit voltage is equals to actual voltage by base voltage, and actual KVLN by base KVLN, actual KVLL by base KVLL. So because actual KVLN into root 3 by root 3 into base KVLN directly gives the actual KVLL by base KVLL. So whether you consider single phase values or three phase values, the per unit voltage will not change. When you go for the base current, base KVA single phase by base voltage KVLN. This is the formula we derived in terms of single phase quantities. Now we will convert these in terms of three phase quantities. We will derive the formula in terms of three phase quantities. So base KVA three phase by 3 and base voltage KVLN by root 3. So if you do this, you will get base KVA three phase by root 3 into base voltage KVLN. So directly by taking the three-phase values, we can directly calculate the base current. We need not again use the single-phase values. So since all the most of the systems are three-phase balanced systems, we need to use the direct data for calculating the base current values. So finally it gives base KVA three-phase by root 3 into base voltage KVLL. Next, the per unit impedance value. So the per unit impedance value initially we have derived in terms of base uh, single phase values. Now we have to convert the base impedance first in terms of three phase values. What the formula we derived is base KVLN whole square by base MVA single phase. So KVLN is KVLL by root 3 and MVA one phase is base MVA by 3. If you do this, so you will get base KVLL whole square by base MVA three phase. This is the formula for calculating the base impedance. So the formula for per unit impedance is equals to actual impedance by base impedance. That is equals to actual impedance is Z by base impedance. The base impedance is base KVLL whole square by base MVA three phase. So the denominator base KVLL whole square comes, and the denominator base MVA three phase comes. So finally, this is the formula for per unit impedance. Actually, computation of per unit impedance with new base values. So when you calculate the per unit impedance values of an equipment based on their own original ratings, so it is confined to that particular equipment only. So for example, if you see this circuit, there is a generator and it is connected a step-up transformer and a transmission line and a step-down transformer and a motor. So here the generator is 40 MVA 11 kV and it is 20%. This 20% is derived based on these two values. Like this, here the transformer Y2Y transformer 20 MVA, it is step-up transformer 11 by 220 kV 15%. It is derived based on these values. So like this, for each and every equipment, the per unit values will have their own base values. So we need to, when you want to solve a complex system, we need to have a common base voltage and a common base MVA. So for that, the per unit impedance in one base is known, we need to calculate two other base values. Here, the Z per unit nu is equals to Z into base MVA three phase nu by base KVLL nu whole square. And Z per unit volt is equals to Z into base MVA three-phase volt by base kVLL volt whole square. So here Z per unit nu by Z per unit volt is equals to Z into base MVA three-phase nu by base kVLL nu whole square into base kVLL volt whole square by Z into base MVA three-phase volt. Now this Z and this Z gets cancelled. The base MVA three-phase by base kVLL nu whole square. Base kVLL volt whole square by base 3 MVA three-phase volt. So now Z per unit nu is equals to Z per unit volt into base MVA three-phase nu by base MVA three-phase volt. So base KVLL volt whole square by base KVLL nu whole square. So in this way, we can convert the per unit impedance in one domain to other domain using this formula. Yes. Finally, we are coming to a very interesting point. Computation of per unit impedance of a single phase transformer. So the per unit impedance advantage greatly lies in computation of this transformer per unit impedance. Generally, when you do computations considering a transformer primary side and secondary side, we need to do all the conversions either from the primary to either to primary side or to the secondary side. But in this case, we need not do like this. The per unit impedance, whether you calculate from the primary side or secondary side, is same. So the entire circuit, you need not bring to either one side for simplification. So that is the greatest advantage of a per unit system, especially in the case of single phase transformer. So the conversion of the impedance Z primary is equals to Z secondary into Vp by Vs whole square. So this is the formula for converting the primary impedance to secondary impedance. Zp is equals to Zs into Vp by Vs whole square. Let us start with this. So we will derive ultimately that Z per unit from the primary side is equals to Z per unit from the secondary side. Zp per unit is equals to Zp by Vp by Ip. So because Z actual by Z base. So Z base can be written as Vp by Ip. So finally Zp per unit is equals to Zp into Ip by Vp. So that is equals to, again Zp can be written as Zs into Vp by Vs whole square into Ip by Vp. So Zp per unit is equals to Zs into Vp into Ip by Vs square. So again we can write Zs Vp into Ip is equals to Vs into Is. So it can be written as Zs into Vs into Is by Vs square. That is equals to Zs into Is by Vs. That is equals to Zs per unit. So finally we can prove like this Zp per unit is equals to Zs per unit. So we have proved that the per unit impedance of the transformer either from the primary side or from the secondary side is equal. This is the greatest advantage. In any circuit, we can calculate the impedance on either side, the per unit impedance on either side, and it is sufficient. We need not bring all the quantities to either primary side or secondary side. That is the greatest advantage of per unit system used in the power system computations. So these are the following references: Stevenson, Junior, William, and Greiner power system analysis, and Wadhwa CL and DAS-D electric power systems. So these are the main references we have considered for developing the content. And thank you very much. And thank you very much.